So Tim Sill with Alpha, and if you don't know, Alpha's out of Ireland. They've been making carrier antennas for a long time. Our competition uses them as well. A lot of people use them. They make great stuff. Tim himself has over 15 years where he worked specifically on the antenna side of the business for Sprint, and I think he'll tell you about some of the other places he worked, because I always like to have people express why they're a credible voice in this particular space. But they've got some really interesting stuff they're doing, and we're working with them as well, especially as we gear up for CBRS and all that sort of thing. So I'll let Tim take it away. He's got about half an hour for some really good content. And thank you, Tim.
Thank you, Patrick. Here we go.
And again, you can advance with that too.
Okay. Yeah, thanks, Patrick and Jesse and Baicells for inviting us here to talk today a little bit about antenna systems in general. Like Patrick said, I've got 16 plus years with Sprint, 21 years in operator space in the wireless network background, and 25 years in RF experience across military stuff as well. My responsibility when I was at Sprint was I did all the base station antenna development and that kind of stuff. So this is kind of right in my wheelhouse on what does it take to make a good antenna viable for your networks. When you start looking at wireless networks, the radio access network is a system. It's an end-to-end system. It's comprised of base station radio filters, cables, everything. And everything has to be designed end-to-end as part of that solution. So when you start looking at trying to match up, the different components, you want to make sure that everything is designed to work together. It's no different than trying to, design a car for a specific need. You got to make sure you put the right requirements together and you build everything end-to-end. If you don't, you're going to end up with a subpar product. RF systems are very critical when it comes to that kind of operation. You got to make sure that your frequency that you spec for your products is all in accordance with what you're needing, making sure your impedance, VISWAR, all those type of things are capable. The actual antenna, even though it sounds kind of unsexy, at least that's the way it was presented in Sprint, it was like, it's just an antenna. But antennas are really critical with the performance of the network and how you design the performance and your actual capability of making sure that you can meet your capacity and coverage or whatever solution you're trying to solve for. Depending on the antenna, it can greatly affect your throughput, the amount of interference and noise that you put into the network itself. Just a little bit of a history. Back in the 80s, we started off with just an Omni, because you just wanted coverage out there because no one really knew anything about wireless networks back then. Then they quickly realized we need to get to panel antennas, vertical polarized type antennas. So those stayed around. They're still around till today, in their rightful applications. When we first built the PCS network in '95, we started off heavily using 90-degree antennas. And by the time we got the first 6 markets built, we realized 90-degree antennas were wrong. We needed to be back at 65 because of the interference it was creating for intercell systems. Then we came out and actually started doing a bunch of innovative stuff where this plus and minus 45, we call them slant 45s. At first we were like, what are these things? But as we got to understand what they were, they dramatically helped us from our deployment standpoints and how we could actually put those on cell sites and make them less obtrusive for the deployments. And it helps you reduce your cost when you're trying to go negotiate with a landlord. It's easier to negotiate a single antenna rather than putting 2 of them at 8, 10 feet apart. Then the evolution of the slant 45, we started introducing electrical tilts. Started off as fixed, then went to variable through a mechanical process, and then we went with a variable with the electrical, manual type of intervention, and then we've gotten into remote electrical tilts, what they call RETs. We then as evolution went along, we found out, hey, there's more and more spectrum out there. Why can't we put different frequencies on the same antennas? So they come out with multi-band antennas. So today, you can have 800, 1900, 2.5, even 3.5 into same antenna packages. Then came MIMO. So now you're really getting into 2x2, 4x4, and 8x8 MIMO. One of the first things that we did at Sprint is that we kind of pioneered the T8R program with the 2.5 network there, and Alpha done a really good job working with us at the time, creating these beamforming antennas. So that was a really state-of-the-art thing. Working through those nuances was very complicated, but they proved in to be very much an advocate to the network and how we actually design the network and the performance of the network themselves. Then we really get into, the full, what we call active antenna solutions. These are the fully combined type of equipment that actually has the radio built right with the antenna itself. And I know that Baicells is working on some of those technologies too. So, depending on your applications, they could be, very applicable. But like in a macro carrier network, they're very expensive and they're very cumbersome, and they really are a challenge for a tier 1 or a tier 2 wireless guy to deploy because of the complexities surrounding making sure you have the right filtering and everything else because of those different spectrum bands. Antennas. So here's kind of a laundry list of antennas information that really drives what is an antenna. Some people think an antenna is an antenna. It's really not. It really needs to be designed to meet your needs, and based upon your needs, you may need something with lower gain, broader beam width, or you might need something higher gain, narrow beam width. One of the good things about an antenna is that it's like a balloon. You push one part of the parameter, it's going to move something else within the parameters itself. So it's a designed system. So you really have to make sure you know your frequency range, what kind of polarization you like. The gain, you can spec an antenna to be, let's say, 19 dBi gain. Well, you might get a 19 dBi gain, but depending on what frequency band you want that to work over, you may have as much as 1.5 or 2 dB loss at the edges of that frequency band. Well, that really impacts the performance of the network when you don't have a nice flat gain across the band itself. The impedance of the antenna, the half power beam width, that's really talking about, right here. It's like when you spec a 65-degree antenna, that's what it's talking about. It's the half power beam width capability of that antenna. Upper lobe suppression and null fill. I've got some slides to talk about that. These are really some of the key things that you really need to take into account when you start looking at antennas, because those can dramatically impact performance. Front to back ratio. That's another one I have some information on too that I'll talk about here in a minute. VISWAR, return loss, those are critical from the standpoint of you have a poor performing antenna, you're going to actually lose power in the system because of the standing wave that you're seeing on the system. So your performance network is going to degrade because of that. If you're looking at polarization, discrimination, slant 45, you got to make sure that slant 45 has discrimination between it. That's what allows you to have the uniqueness between the two different ports. Beam squint, that's really the amount of area you have from the bore site. So if it says 0 degrees, then your beam squint is a margin of error that says it needs to be within a certain parameter there. The beam tilt, so you have the, how much down tilt you have in your E field there. And that can be done either mechanically or electrically. And I've got some slides on that to really show you visually what does that really mean and how does that affect the network. Then you have what we call passive intermod. On a TDD system, you don't need to really worry too much about it. And when you're talking about FDD systems, passive intermod is a big issue, especially when you start layering on multi-frequencies. It can become very detrimental to performance. And then, of course, last but not least is the material and environmentals. You know, what kind of materials do you want your antenna made out of? That can really matter a lot in how the performance of the antenna is over time. Because the last thing you want to do is pay a tower crew or somebody else to go out there and put your antennas up, and a year and a half from now go out and have to remove and replace them because of corrosion, water intrusion, those type of things. So a lot of key things to take into account when it comes to the unsexy antenna. The slide here is really to help emphasize, you know, upper side lobes. When you start talking about upper side lobe suppression, it's really being able to take and design an antenna that takes care of this area here. Here's an optimized pattern, and here is one without it. And what happens is when you actually go deploy an antenna and you put some, let's say, mechanical down tilt into the system, all of a sudden, if you have all this unoptimized power up here, now it becomes an interferer for the cells next to you. So that in itself will now create a bunch of noise in the adjacent cell. That will dramatically impact your performance from a throughput, capability, and capacity. Another key item here is the null fill. So this optimized pattern right here versus right here is these little valleys right here create coverages of you don't have performance, you don't have coverage in those areas. So having that null fill in there really allows you to take care of the stuff closer to the cell site itself. Here's one for you, all you geeky engineer kind of guys like me. So this is a 3D model of the optimized pattern here versus the non-optimized pattern. It's kind of hard to see on the chart here, but it gives you kind of a gauge here on what's really trying to do here. But the key thing is you can really see how further back the different lobes are, and then how fat this is compared to this one here. So that when you get that into the network, all of this energy up here that you don't want into the other network, you know, you want that pulled back, where this is going to become a bigger issue for you when you start actually trying to deploy a non-optimized type of antenna. Here's a little more rudimentary type of an approach. You know, the one on the top here is, again, that's your upper side lobe. That's where it's going to get over into your next cell site away, or multiple cell sites. When we first started deploying some antennas at Sprint, we actually had some antennas that came in that didn't meet our spec after we had tested them. So during the manufacturing process, they stopped looking at their antennas and they actually started introducing a bunch of upper side lobes. And through testing, we found all of these issues where we actually saw interference as much as 10 miles away from sites that were 3 tiers away. And then as we started digging into it, we took some down and actually took it to a range and found out that through the manufacturing process, they didn't keep the same criteria and quality in the antenna pattern design. So all of a sudden it created all this interference in the network. Once we went through and cleaned up all those antennas, we saw like a 40% performance gain in the network because of just that particular issue. And again, the big thing here for near cell is, you know, making sure you have a good null fill to cover those customers that are in closer, that you're not shooting over the top of them. On return loss, you know, this is another key item to make sure when you start looking at your antennas to make sure that you spec out the right VisWAR capabilities. You know, you're talking about, you know, the amount of power, it's all about matching the impedance of the actual complete system. If this is not matched up, you will get a voltage standing wave in there that will actually create issues. You see antennas that are, you know, spec'd at 2 on the VisWAR level, you're going to lose about a half a dB in your output power of the system because of just that antenna itself. If you have cables that are not high quality cables, you know, they'll do the same thing. They'll cause a dramatic impact on your overall system performance. Another item that will have a dramatic effect on this is proper weatherproofing at the antenna or at the radio input. If you don't have the right weatherproofing on there, any type of moisture intrusion there creates standing waves into the issue. So you have to make sure that it's a complete system, sealed up tight. If you don't, over time, it will degrade and take out a lot of the performance of your network. The bad thing is a lot of times these things it's a slow fade to gray, to black. You don't see it happen overnight. It's just like all of a sudden you start seeing, degradation of the performance. It might be a year from now. But if you go back to a year prior and look at the performance that you have, then you'll see it. But most tools don't take that type of an approach and look at it. So it's an important thing to make sure that those are taken into account to make sure that that the performance of the network stays true. The half power beam width, and for both elevation and horizontal, the azimuth, is just like I said earlier. It's a function of the actual variation of 3 dB from your peak point. So when you're speccing an antenna, that's really what you're talking about. You're saying, okay, I want my 3 dB point to be at a certain particular specification, and then you can actually go test it. And when I worked at Sprint, we actually did this on every one of our antennas, and then we'd spot check them too, just to make sure the quality was there. And once we got comfortable with the company, we knew that they had a good quality program in place and they were testing it. We had a lot of of capability of saying, yeah, if I have to go talk to my senior guy, I know my antennas are right because these guys have the right testing in place, and they provide us with spec sheets to make sure that when they get it, we know exactly what the performance of that antenna was when it left the factory. So that's, it's critical to know what kind of variations that you can get into these areas. Okay, front to back ratios. The front to back ratio is critical too. If you have a poor performing front to back ratio, that's the energy that you're seeing splash here from behind. The antennas are made up of multiple arrays, and they have a reflector on the back of the antenna. If your antenna reflector is not performing like it should to help keep energy in the front, it'll allow energy to go behind it. If you're doing a 4-sector type of deployment, you can actually introduce noise from one sector into the other one very easily if this front to back ratio is poorly performing. A good performing antenna is 30 dB down, because if you're putting two antennas close together and you got if it's 15 dB down, all of a sudden now you're putting a bunch of noise into that radio next to you. That's going to dramatically decrease the performance of that particular system. I touched a little bit on this earlier, the cross polarization discrimination. That's really about the slant 45 antennas. That's making sure that your different poles themselves are discriminant, so they're independent from one another. And this is a pattern here of what it looks like when you have one polar measurement, and you can see the copolar side over here is way down. So that's telling you you have a good isolation in that antenna, and there's going to be a good probability that from a receive diversity standpoint, you're going to get your gains that you're looking for around 3 dB. Electrical tilt, so tilts in general. This is another very key area to think about when you're designing your systems. When you look at the antenna system, it's a subset of the overall network, and it's a small part of it, but it's a critical part of it. And when they introduced electrical tilt, we were kind of like, well, how does this work? So as we went through and started doing the testing, we really understood the value of electrical tilt versus mechanical tilt. I have a slide coming up next which will really depict that for you visually on what it means. But it started out, this is an external rep motor that will allow you to adjust an antenna, or it can be a manual, but it gives you the capability to optimize your network based upon whatever conditions are. You may start off with a network that you want coverage. And then once you start loading up the network, you can go in and do what we call a cell split, where you actually come in and will physically put another station in between other sectors. Well, you have to do something with the energy of the sites around it. One way of doing that is to down tilt it, move it out of the way, or drop the center lines. And with a variable electrical tilt, it gives you that capability, so you don't have to physically go out and change the antenna. And it can get costly when you change the antenna. You start talking about a tower crew and all those different attributes of the cost it takes to go do those changes. Here's what a mechanical tilt versus an electrical tilt looks like. You have this blooming effect over here when you start talking about a mechanical deviation, because that's actually, when you push that antenna down, the pattern doesn't change from the antenna, but it changes the way it's hitting the ground. And what happens is you get this ballooning effect to where you actually really change the pattern. So you get a pretty heavy degradation in your overall coverage and your performance. And a lot of people don't really realize that until you see a visualization of this type of pattern design. With electrical, you're doing exactly what the pattern looks like originally, but you're just pulling it back through what we call phase shifters. And that's how an antenna works, is that, based upon the design of the different elements in the array, and the phasing of it will allow you to be able to down tilt it or leave it up, or up tilt it, or whatever you want to do. So it's very critical. When you're looking at networks, you can design in some mechanical tilt to some extent, but you get too much, you're going to actually really balloon that pattern.
These patterns, now, are these taken from the same radio or the same demonstration?
Now, this is an antenna pattern, so this is just if you run it through an antenna range, an anechoic chamber, you can actually measure this type of performance impact. Yeah, the radio is immaterial of the antenna itself at this point. This is an RF propagation effect that happens. So, like I was saying earlier, when you're talking about an antenna pattern, it's a balloon. You push something else has to give. When you start talking about using phasing, so here's an original antenna here with 0 down tilt. And you can see where, we have the null filling here, and the, at least 18 dB down up here. We spec'd ours at Sprint over 20 to make sure that we could control that interference out into the far field. But then when you start adding in some tilt, and you get 5 degrees down tilt, that's a pretty good down tilt. With the phaser, what it does, it's shooting that extra reflective energy up. And that energy there will never get into the cell site around you. It's going to be shooting it up into the sky. So it helps you control that interference. And then here's a chart here with 10 degrees, so it can really show you how that right there can really get morphed. And that right there, if you had that projected into the adjacent cell or two tiers out, you could really understand why the performance of those cells all of a sudden would start degrading, because you have all that extra noise into those different areas. And that's very detrimental for LTE networks, or any type of communication network, actually. Pattern overlaps. This is another one, that depending on how you deploy your systems, if you're using an n=1 type of combination, here's a kind of a depiction of a 65-degree beam width overlap versus a 90. You can really see the overlap patterns right here on the intercell overlap. So, it's using a 90-degree antenna is not always good. If you had an n=3 combination, this right here would be really good. But you have to be careful in those type of conditions, because we've seen when we were doing stuff on the WiMAX systems, when you had an n=3, if you didn't have enough channel separation between your channels, you could actually run into degradation in the performance of these intercells because of the spacing of the frequencies too. So you have to make sure you have some good isolation between those different cell sectors to ensure that you have the right performance that you're looking for. You know, and depending on the radio specs that you're using, you know, it may be able to tolerate that or it may not. So again, it's an end-to-end design, end-to-end solution. You just have to make sure that you take that all into account as you're looking at the system as a whole. Let's see here. Yeah, so that's key. Here's a, no, it actually turned out pretty good. I was kind of concerned about this chart. So here's another way, like if you're, you know, the previous ones we're talking about, you know, just kind of coverage. When you get into situations where you have some hotspot locations, you know, it costs you money as an operator to go put a new cell site in, unless you have somebody that's going to allow you to go put it on their property for free, which not all of us have. Here's a combination or an option. This is a high capacity twin beam product that Alpha actually offers, but it's really set up nicely to be able to allow an operator to come in and just replace the antenna, a 65-degree antenna, or 90, whatever you have in place now. And this twin beam system here is set up with 233s. So if you're doing an n=2 deployment, you would basically have these different sectors here all on n=1, and then you'd have the opposites here on n=2. And you know, with the right network configurations and stuff, you can actually get 2 times the capacity of that cell site. Now, if you're using an n=1 configuration and you have the capabilities of using, you know, comp and EICIC and some of the LTEA features, you'll probably get 70–75% gain out of that type of a combination. But the interesting part about this approach is that a lot of times you can go in and do this and kind of fly under the radar with your different landlords by saying, I'm just doing an antenna replacement, and you're able to put these other antennas in here and then do a radio swap that will allow you to be able to take on multi-carrier technology, and you can go in there and double the actual capacity of the network. And if you do it right, I mean, you can do it without an increase in your OpEx for your monthly rates. So it's an interesting concept. Again, you have to design to the needs. You know, you wouldn't put something like this everywhere, just like you wouldn't put a 90-degree anywhere, 90-degree or a 65 everywhere. So it really varies from what solution are you needing to solve what problem. Another approach to coverage, you know, rather than a panel type of antenna, you can go to omnis. There's 2x2 and 4x4 MIMO omni antenna solutions out. You know, it leverages the slant 45 technology. It allows you to put everything in a nice small canister. You know, it's down as much as 4.5 inches in diameter. And it's a good way to go in and put in a small cell where you have a single radio, and it gets you 360 degrees. You know, get you 8.5 dB gain or so. You know, or if you're stuck in an area that you know, the municipalities don't want to see big gaudy antennas, you know, these can be set up to have independent down tilt for each sector. They could have what we call a pseudo omni, where you have one radio that runs them out, or you have 3 sectors all built into this same combination. But the key thing is making sure that your patterns are very well flat across all of the sectors, and allows you to fill in the areas that you need to cover. You know, it's kind of difficult to see what, you know, all of the different lines are here, but this is a, you know, multi-frequency sweep across this particular antenna as we rotate it through an actual anechoic chamber. So those are, you know, tools in the toolbox, as we used to say, you know, and it gives you capabilities to do different things. You could do, you know, one of these for pure coverage, or put them down low and do small cells with high capacity. And then last but not least is we have the antenna materials. You know, when you start talking about materials, you know, it can dramatically affect the performance of the antenna over time. if you start out with stainless steel versus hot dip galvanized, I mean, it's kind of, over time, hot dip galvanized around, the coastlines are gonna oxidize on you. We've seen it all the time. So, we ended up started speccing out stainless steel. PVC versus fiberglass, it all drives in the end, what is the cost of the product and how does it perform over time. And you really don't want to be investing and reinvesting in products as you operate a network, because that's not going to be profitable or beneficial for you in the end. And then another key thing too is, sealing of the antenna. When we first started deploying antennas, we always spec that those things need to be sealed. And about 3 years into it, we started having a huge number of issues up in Des Moines and Minneapolis and stuff like that, and we couldn't figure out why. So one of our guys up there pulled an antenna down we had, and we cut it apart, and as soon as we cut it apart, there's water all over the inside of it, and we couldn't figure out why. And what we ended up determining, well, this is just the temperature variations between hot and cold was allowing moisture to get in there and then not getting back out. So over time, it just kept building up that moisture and creating an issue. So most of the antennas, all of them that we spec, for our customers and stuff, all have a hole at the bottom that allows any type of air to move in and out, so you don't have that potential issue. So, questions?
One thing I've been trying to encourage all tower manufacturers that'll help the WISP market is to include or make available engineering drawings to send to tower companies, things like that. So when they do the quotes on the towers and things, they don't have to make up their own from 3 or 4 different sources. So I just want to make a comment that would help this community quite a bit.
Yeah. Yeah, it is. It's good to standardize that, so when you go in and see your community, you deliver a consistent package to them. They get more comfortable with your approach in doing that, and that's one thing that that we do with our systems, that we try to produce our antennas, and we'll provide it with a mounting bracket system, so you don't have to worry about do I need to go buy the mounting brackets and everything else. No, it comes together, so that way it's a system that's ready to go for you to put on the network.
I have a question for you. So we do slants, and I've heard, and I'm the least technical person standing in this room, but I've heard some of the opinion that for LT, slant is better than HRV. Do you have any opinions on that, and if so, why?
We actually did a lot of testing in that area, and all of our testing, we actually had a gal at work for us she was a PhD, and she ran us through the ringers on this, and we put a lot of theory behind it, and all the testing we came up with between doing spatial diversity with HV versus slants was within 1/4 of a dB, and we just did not see the difference. It was, as long as you have the discrimination between your polarizations, you're fine. That was the key.
Very good. You have a question over here?
Specifically with the Baicells equipment being heavily focused on 2.5 and 3.65, do you have a dual antenna specifically targeting those 2 frequencies?
Yeah, we have a broadband solution. Jason's our sales guy back there. I know he's got all those numbers memorized off the top of his head, but yeah, we do have some broadband 2.5 to 3.5 products.
Gotta love it when the engineer is smart enough not to get too much in the commercial side.
Yeah.
We knew this was coming. We got a question over here. Yeah, I thought about it.
Whenever you say broadband, is it one antenna that covers both bands, or you can actually feed 2 separate feeds into that, where we can do 2 radios on a single antenna?
Jason, do you remember off the top of your head? I know for a fact we do have we have a combination. It'll cover from 2.65 all the way to 3 or 3.7, in one array. And I think, do we have 2 port for each that does a internal diplexing. You remember? Yeah.
Yeah. One of the things we're looking at is, you know, if you can hang one antenna, a lot of the tower rental place, you know, they charge you per antenna. So if you can put 2 radios on a single antenna, you're 50% more efficient.
Yeah.
Well, that's a nice segue into our next presenter as well.
Yep.
So, I'd like to thank Alpha for coming in here and giving us some of their time, and I appreciate that you kept it technical and everything.
All right. Thank you, guys.